Hello, Professor Sean.
Hello,
Can you
Professor.
hear me?
Yes, I can hear you. Can you hear me?
Yes, please. So, first of all, welcome to this particular session and uh, welcome from all of us here in India, precisely to be in Roorkee. And there are a large number of participants, as well as in the participants, we have so many young and lovely faces, men and women, and we have many resource persons here, all waiting to listen to you. Okay, so uh, as per the time schedule worked out by Professor Deka, so we plan to have this particular presentation of yours from 10:45 to 11:30. Okay, so I think if you can finish about 5 minutes early, it will leave us some time for question and answers. So please allow me to introduce you to this gathering. Thank you. So, friends, Professor Sean is a director of Australian Research Council Research Hub for Nutrients in a Circular Economy, head of discipline, environmental and water engineering, and deputy director, founding member of the Center for Technology in Water and Wastewater Treatment at the UTS, University of Technology, Sydney. His research interests include a circular economy, membrane technologies, water treatment processes for water reuse and desalination, resource recovery and environmental nanomaterials, physico-chemical processes, and environmental applications. Since 2000, he is externally engaged as an ARC College of Experts member and editor in chief of the Desalination Journal. He has co authored one book, 31 book chapters, over 510 refereed journal articles, and three patents, cumulatively receiving over 20,000 plus citations, resulting in an H index of 72. Over the last 20 years, he has successfully attracted numerous projects to UTS from the ARC and industry partners, including an ARC Future Fellowship 2015-2020. And surprisingly, I had got an opportunity to visit UTS during my Endeavor exchange program. So that it's I've been to UTS, but yes, it has been a pleasure to invite you for this particular workshop. So you may kindly start your address. Thank you very much.
Thank you, Professor. Thank you, everybody, to invite me this MEMDEW conference. So I'm very happy to share our research activity, desalination, and resource recovery using membrane capacitive deionization. So these are outlines. I will briefly mention about desalination and brine mining with MCDI, and then I like to recover today uh, bromide, bromine, and lithium and rubidium, three compounds in seawater and seawater brine. So already everybody knows seawater is a reliable water, food, mineral and energy resources. So we have a lot of salt dissolved in this seawater. Also seawater functioning as oxygen level of the air, because a lot of people mention about that the Amazon is one of the lung of our oxygen concentration contributor, but seawater, because of the seaweed, almost more than 60-70% of the oxygen is from the seawater. So seawater is very much important also our CO2 balance, as well as a lot of benefit to our lives. If you look at the concentration, so sodium chloride followed by calcium magnesium sulfate, and a lot of minor constituents. So how we can recover this material, and then we can desalinate, which is one of our sustainable water resources. So if you look at the desalination in the world, so this is the overall global seawater reverse osmosis capacity. So Saudi Arabia, also we have India here, but I believe there will be more expansion of this seawater desalination plant because a lot of population, we need more water in the future. So if you look at the growth rate of the seawater reverse osmosis, brackish water reverse osmosis, and then thermal reverse osmosis, so SWRO is increasing compared to our thermal desalination. So overall, the SWRO and BWRO, so it costs around $6 billion per annum. So we need around 6 billion or so. This is only capital cost. If you consider OPEX, so OPEX is the double of this capital cost, which means $18 billion required to maintain all the desalination plant. So this is a huge amount of money, so that a lot of people try to reduce in terms of capital cost and OPEX, especially energy cost. So if you just save the 1 kWh, so it will really impact the overall our CO2 as well as the energy consumption. So there are a lot of effort. We are trying to develop more sustainable and cost-effective desalination. And if you have a desalination plant, so this is seawater and seawater brine after desalinated water. So still there are a lot of leftover. So sodium, calcium, magnesium, and then different monovalent ions is in brine. So this brine can be mined and try to convert to the useful material. So you can see the brine water can simply produce the calcium carbonate. Also, they can be separated with nanofiltration technology. So can separate multivalent ion, monovalent ion, and then multivalent ion we can recover magnesium hydroxide. Also, there are a lot of useful material, indium and vanadium, gallium. So we can collect this kind of useful element from brine. So we can utilize the polymer ionic membrane selective, also 3D absorption module using some of the solvent extraction method. Also iron liquid can be used. If you look at the monovalent ions, so you can have some of the advanced multi-effect distillation to have a further desalinated water, and then remaining monovalent ion can be extract further using solvent extraction, also some of the polymer ionic membrane and the 3D absorption module, electrodialysis by polymer with improved ion exchange membrane. So ultimately, we like to collect rubidium, boron, lithium, or some of the byproduct. So we can collect the useful element from brine, which can have an extra income from the desalination plant, so that we can cover some of the very huge expensive capital and OPEX cost. So if you look at the detailed mineral, which kind of mineral will be more cost effective to recover. So this red zone, rubidium, lithium, bromine, and magnesium are the most viable element to collect from the RO brine. In particular, this magnesium is very much simple compared to other monovalent ion because this can be separated by the nanofiltration. So sodium and magnesium and different balance can be separated by nanofiltration membrane. So I don't want to discuss about nanofiltration. Also, this nanofiltration separation has been commercialized by Neom, and then they are actively collecting this magnesium compound. And today I like to focus on rubidium, lithium, and bromide, how we can recover these three elements using membrane capacitive deionization. So briefly, I like to introduce the capacitive deionization. So this is the emerging technology, highly suitable for low sunlight, relatively fast process, efficient removal of charged ion, ideal for decentralized small-scale system. So we have a graphite seed and carbon electrode, which is powder activated carbon, and spacer, which is the water channel, and we have an electrode and a graphite seed. So we have a direct content, plus to minus, and then you can separate your ion. So this is the membrane capacitive deionization. So just attach the cationic membrane, anionic membrane, and just to pass through your ion, positive and negative ion can be collected from this electrode using very low voltage and low pressure, chemical free, and then this can be separative, and we can have also very much desorption stage. So using source circuit and reverse polarity or chemical pre-process and energy recovery, also focus on the resource recovery, can be achieved this MCDI system. So there are a lot of research going on to develop better electrodes, such as carbon aerosol, graphene material, or Maxim can be utilized as a good electrodes. Also application side, energy saving as well as processes. And this is the application. People try to apply brackish water, which make your drinking water quality less than 500 milligram per liter. Also water softening to remove some of the calcium, magnesium, also remove the arsenic. So some of the contaminant arsenic or specifically nitrate in groundwater, and they are less tedious, but the problem is the toxic heavy metal and nitrate compound can be only removed specifically using this MCDI technology. So this is the more cost-effective process. So we have collaborated with the Korea project to demonstrate the seawater desalination after first RO, and we connected with the second path RO, and this is the in general RO process, and we try to replace with this RO second pass to MCDI, and then saved almost zero point 0.3 kilowatt hour per cubic meter, and we can have a huge amount of energy can be saved from this process, and we demonstrate this 1,000 cubic meter per day of the energy efficient desalination in Arab Emirates, and successfully we uh, install this process and demonstrate. Also, we are helping this MCDI technology with the solar panel in Tuvalu. Tuvalu is located in this area, and they have a significant impact from the climate change, the sea level rise, and they have a little bit of seawater penetrate the groundwater, so drinking water is not enough. So that we try to connect with the PV panel with seawater RO and CDI process to provide carbon zero our desalination technology. And first challenge, as I mentioned, I tackled the three element recovery in this study. The first one is the bromide. So we have published around 10 papers for last uh, 7 years to recover this bromide. So bromine market is value of the USD $3.6 billion, and market is growing 5% between 2021 and 2026, and it will reach to 4.5 billion by 2026. Mainly used dye production, flame retardant, and pharmaceutical, agriculture chemical, and insecticide, pharmaceutical chemical intermediates. So there are a huge amount of bromine is utilized. So what we try to recover bromine at this stage. So this is the schematic from the Neom city. They like to commercialize this technology. So first they want to collect the 1 million cubic meter per day of the seawater intake, and pre-treatment nanofiltration can recover a lot of divalent and trivalent, and monovalent pass through the seawater RO, BWRO, and then drinking water produced. At the same time, they collect the divalent and some of the monovalent ion to pass through the membrane, brine concentrator, and crystalline, and try to uh, collect the bromine in this process, which is almost 4,000 ton per day, which is a huge amount of bromine, but still they have a technical issue to effectively recover this bromine, so that we have tried to combine with our MCDI to recover bromide removal. So look at the TDS effect. So when you have a TDS, this concentration, your bromide removal decreased when you have a background water is more salty. And then we have developed how we can specifically select our bromine concentration, and we combine our activated carbon electrodes and then put this bromide resin and then covered on the top of our ion exchange membrane. So anion exchange membrane polymer plus bromide selective resin we have mixed together and then produced this electrode with the bromine selective electro compound. And then we tested the stability, and then looks like this MCDI has a very good stability. And look at the bromide absorption. So bromine, bromide, the difference is if you oxidize the bromide, so you can convert to bromine. So Br minus convert to Br2, so that you can collect the bromine with the chlorination. So that's the reason why in the seawater it present as a bromide. So we need to also first recover this bromide. If you look at the chloride and bromide, so this is the without any uh, component of the bromide MCDI and the bromide MCDI. So you can see the bromide MCDI is red color, and then this pink color is the bromide MCDI. So overall bromide selectivity is almost 3.4 times higher than just the normal MCDI. So we have increased overall our bromide selectivity using our bromide MCDI. So we compare with the different chloride, bromide, sulfate, nitrate, iodide. So bromide selectivity was almost 10 times higher compared to the just the normal MCDI. So that's the what we have developed for the bromine recovery, and try to have a more real water sample test. And next challenge is the lithium. So we have also worked this area for last 5 years to recover lithium from seawater. So I just want to skip the general background of lithium and lithium inland exploration. So Chile, Argentina, and other countries, and they have a lot of the lithium on land, but it has only 22 million tons. However, in seawater, lithium concentration is almost zero point 0.2 milligram per liter, which is 230 billion ton, which means it's almost 1,000 times more lithium concentration contained in seawater. So what happened is the challenge. So extracting lithium from concentrated seawater is not straightforward because major ions, sodium, magnesium, calcium, potassium are present in significantly higher concentration lithium in seawater. So how we can selectively collect this lithium? So we investigate some of the technology. So lithium manganese oxide, titanium oxide, manganese titanium oxide is ion sieving method is one of the commercial technology. And then electrochemical process MCDI or hybrid CDI can be utilized. So we like to combine these two technology to effectively collect our lithium compound. So if you look at the ion selective lithium material. So inorganic, organic, polymer, crown is natural material. So you can see the different material can have more selective your lithium, especially this UIO 66 HQST GIF8 have very strong absorption capacity with lithium in seawater, and this is our commercially available lithium ion sieve method. So if you see the lithium ion selective structure, the hydrogen can replace with lithium, and then you can have also lithium can replace with this hydrogen. So in your lithium ion selective absorbent, so you can simply exchange your hydrogen with lithium so that you can have more high concentration of lithium from this lithium ion selective absorbent. So aluminum based, so you have a very strong merit for this performance. Then selectivity wise, manganese lithium oxide has a very strong selectivity, and titanium lithium absorption capacity has a very strong performance from these three metal absorbents. So we have developed MOF-based electro for selective lithium recovery from aqueous solution by using MCDI system. So this study published this year, both of paper. So I want to share this result. So we covered our material GIF on the top of the activated carbon and tried to selectively pass through only lithium ions through this cationic ion exchange membrane and GIF, and that's the how we can have a more selective lithium concentration. So we have compared with different ions, so GIF material coating based on the previous absorbent, which has a very high selectivity. So how we can have a good electrosorption method. So we have tested this basic MCDI setup. This is the activated carbon, powered activated carbon, and this is our GIF8 in situ growth on the top of this activated carbon. So you can see the activated carbon and GIF coated electrodes, and we put the cationic exchange polymer, and then we create the GIF8 polymer membrane coated electrodes. So how this will perform different tests. So this is the more larger same image, the double coating with GIF, and this is coated with the ion change membrane. So we compare the result with this electrographite activate carbon. This is the first scenario. Second scenario is the GIF8 we incorporate on the top of activate carbon. So third scenario is that we put the only ion change membrane and then GIF and ion change membrane. So first scenario we compare with how much we can improve the overall lithium selectivity using this MCDI. So before coating and after coating, so we compare the different lithium and sodium removal and the potassium. So we found out overall the lithium selectivity shifted from zero point 0.7 so after coating, and we found 3 for sodium and zero point 0.4 to 1.4 potassium. So we have increased the overall selectivity of the lithium from this uh, MCDI. Also, we compare with the monodivalent ion magnesium and calcium. So it changed to 0.68 to 0.65 and 0.5 to 0.46. So when you have divalent ion, so lithium selectivity was not really high compared to the overall their monovalent ion. So this is the summary of the competing ions with the lithium and sodium and the lithium potassium after lithium selectivity increased, but magnesium calcium overall it decreased. So we also compare scenario 1 and scenario 2 and scenario 3 and scenario 4. So overall we have increased with sodium potassium in general when you have GIF, and then 3 1.18 when you have this cationic membrane on the top of GIF and activate carbon 1.3 1.18. So when you have GIF, it has better selectivity. So this is the removal mechanism. This is the what happened is the competing with the monovalent ion. So lithium crossed over the GIF8 and then coating with the subsequent partial hydration and dehydration due to favorable ion size and superior charge density. And dominant removal mechanism, so lithium is the more of an electroabsorption we can achieve, and sodium, calcium, magnesium, and potassium. So coulombic and van der Waals attraction had a more removal mechanism for this material of the MCDI with GIF. So GIF has a very uh, useful material to increase the overall selectivity of the lithium in seawater brine. And based on these two elements, also we look at the rubidium. So how much rubidium is inside in seawater is around 0.2 milligram per liter, which is very similar to lithium concentration. So how we can collect this rubidium from seawater? So we have a good uh, use of this rubidium application with the high precision laser for naval submarines, a medical application, CT scan, and rubidium quantum navigator for ships and submarines. So that's why reason the rubidium is becoming more and more critical mineral because they can use many different advanced high-tech application. The problem is there is no such land or rock mining of rubidium, and mostly they are attached with some of the ore. That's the reason why you cannot collect a huge amount of the rubidium compound. And on the other hand, the seawater mining, so rubidium concentration is 0.2 milligram per liter, which means 2,300 billion of the ton of your rubidium is contained in seawater. So how we can collect this rubidium from seawater? So we like to introduce this selective rubidium recovery using potassium, cobalt, hexanoperite ion exchange in nanomaterial. So we have this material, potassium can be replaced with rubidium for ion exchange mechanism, so that we have developed this KCOFC, and then look at how much rubidium can be recovered from seawater brine. So this is surface charge. We have designed for attract positive cations on each surface. So this is the potassium and rubidium go inside and then release the potassium, and then they structured inside this KCOFC with the rubidium compound. So we can have this kind of mm, uh, regeneration using the potassium. So you can have rubidium with very high concentration. And this is the structural image, and we have also ionic radius material. So if you look at the rubidium and lithium, and they are our target compound. So if you see the radius size is 1.48, so lithium is 0.66. So if you see the how this compound can be collected from this structural ion chain, and then we measure the basic absorption experiment. So you can see the rubidium observed capacity is almost 100 milligram per gram, which is the good capacity of this absorbent. Then when you have increased your sodium concentration, and then your rubidium recovery is a little bit decreased around 10 to 15%, but still, so it's a manageable level of your lithium compound. So we compare the recovery with lithium, rubidium, and rubidium magnesium, and rubidium potassium, and rubidium seawater. So rubidium potassium. So when you have a replacement with rubidium and KCOFC, so you can have your recovery is relatively low, and then you are also after your regeneration. Also, we have to effectively remove this potassium. So potassium and rubidium separation will be one of those challenges to utilize this process. And you can see how this metal organic frame can improve the overall KCOFC. So this material we have incorporated with those both compound. So based on our experience, the GIF material has a very specific channel to pass through the radium, and that rubidium is very much similar for the ionic side we can try to maintain. And then we have combined with the KCOFC and this MOF compound, especially GIF, and how we can improve the overall uh, recovery of this rubidium compound in seawater. So we have combining together, and then let them observe on the surface of this KCOFC, and then we tested this compound. So how much over KCF, and then KCFS GIF. So rubidium compound, they are both relatively good. And then when you have rubidium uptake capacity in seawater, and then overall KCOFC, and then KCOFC surrounded by with GIF, and you have almost 8 times higher rubidium uptake we have achieved compared with GIF only. So GIF only is just pass through and that they cannot uh, keep the inside your case, your FC material. So that's the how we can utilize the overall this the KCOFC combined with the GIF material will improve the overall recovery of the your rubidium recovery. So you can see that this is the time image of the KCOFC. So we have coated with this GIF material and surrounded this. And then we found out what kind of compounds is well distributed for this design of the nanomaterial. So we successfully and then replaced with this rubidium with the potassium, and then we have a better recovery rate. So if you have a KCO and GIF, then when you have this rubidium with hydrate, then go through the GIF dehydrate and then replace this potassium, and the potassium will be discharged, and this rubidium will be stored in this nanomaterial. So that's the what we have developed, and then we try to create the polymer encapsulation to apply for the seawater brine column test. So we have successfully utilized this absorption desorption test. And then next step is we want to have spec membrane with this MCDI technology. So we want to have our polymer with this KCOFC and the MOF material. So we can combine with our cation exchange membrane, and then we can have a selectivity with the rubidium, and then have a better way of the regeneration. So when you use the simple absorption desorption, you have a potassium problem, so we have to additional separation process. But if we use the MCDI, so we can have directly we can observe on the rubidium and then dissolve this rubidium compound. So that's the what we are trying to develop this material. So this is the seawater and KCF GIF membrane, and then rubidium compound only can pass through this flow CDI system. So FCDI can continuously create the rubidium concentration, which is the very high valued material using this FCDI process. So you want to combine this, you want brine with the flow system for the continuous system, and then we can collect with the rubidium. Also, we are trying to develop the lithium as well, which can be used for critical mineral, and that's what we are planning to do for seawater mining with the nanomaterial and then move compound using electrochemical process. So final marks, the brine mining becomes more important to recover critical minerals. Brine, rubidium can be selectively recovered using MCDI. MCDI has very uh, useful electrosorption mechanism, size exclusion, van der Waals, and the Coulombic play a vital role, while target ion possesses the less charge density compared to the competing ion. So future bromide, lithium, rubidium capturing system need to focus more larger scale, as well as the optimized process can be developed to make commercial opportunity in the future. And I'd like to thank you, DECA, for kind invitation. Also, this MEMDEW organizing committee, also our AIC funding, and Korean projects of United Nations, also Sean Tech. Thank you for your attention.
Thank you, Professor Sean, for illuminating and a very, very interesting lecture. May I now check whether the audience have few questions to Professor Sean? We can take one or two questions. Anyone in the audience, please? Okay, there seems to be one question. Can you please pass on the mic to her? Please tell your name and your affiliation and then go ahead with the question. Thank you.
Hello, Professor. My name is Ayushi Kapoor, and I work on membrane-based separations for the food components. My question is, can the process that you have explained be applicable to other complex matrix like food products, food products, to isolate these chemical components?
That's a very good question. So just let me share this one, and I like to. So if you see this process, can you see the bromine resource recovery from SWR brine slide?
Yes, sir.
Yeah. Okay. So this is the what we can see the overall your competing ion separation. So you never use directly all the complicated your feed water. So as you can be see, even seawater brine, so they need to go through the nanofiltration, they need to go through the membrane, brine, concentrator, crystallizer. So in your food feed water or whatever you have, so you need a specific pretreatment process because every water, every solid, they have their own way of the separation technology. So we have, right? So that
Yes.
you don't have to separate directly one technology. It can be combined as a several technology so that finally you can increase the overall your selectivity from your designed feed water sources. So don't worry about only one technology. We can use this MCDI. Yes, you can do, but depending on your water quality, so we can utilize several separation technology to achieve the more high concentration of your overall targeted ions.
Thank you.
Thank you.
Any other question from the audience? Okay, Professor Sean, I have just a very small query to you.
Yeah.
As I can understand from your presentation, that the resource recovery, especially with respect to bromide, lithium, rubidium type of elements, which are very crucial, and they have been attempted at the pilot stage at your site, right? So, have you been able to do some life cycle analysis of these processes so that we can then actually bring in them into the commercial domain?
Okay, that's the very good question, which is the always the problem of the real commercialization opportunity for every at cutting edge technology. So what happened is this is the same, life cycle assessment has to be done even though you have a very good life cycle assessment, techno-economic analysis, and then you have a lot of benefit to your technology. But the problem is supply chain. At this moment, we have enough critical mineral supply chain system that we have to compete with the traditional supply chain. For example, like we produce a lot of salt from seawater brine. However, the seawater brine salt, even though we produce a lot, but the existing traditional way of you're producing the sea salt is they have also their own supply chain. So we have to compete with this kind of supply chain. And then this critical mineral is the same. At this moment, we don't have very much clear supply chain because of the impurity and purity issue. So that also we need to have a little bit more clear supply chain. Who will buy this material? Who will manufacture more high purity, and then how this can be applied? Because already traditional market and supply chain, they have their own supply chain and then life cycle assessment. So that we need to take a time to get together with the only like technology side. So we need also some people who can purchase, who will do more selling and then marketing, or also you can have a clear supply chain to have a good flow of the this recovered system element. So that's the we want to develop in the future, because Neom City and they have this technology, and then they are now trying to contact the how we can compete with the traditional way of the market with this produced from the seawater, brine, and critical element. So that's the what we have to do next stage. And your question is definitely that's the most important when you created a commercial opportunity in the future, uh, our
Yeah.
developed technologies.
Yeah, thank you, Professor. One thing, just I'd like to ask about your vision, because being an academic and trying to work out technologies for commercial purposes, what is your take in future? For example, you develop this particular technology of bringing it out through brines in comparison to the real strong mining lobbies which have strong cartels for the governments. So basically it could be a fight between the academia based turned technicians into those particular cartels where they have huge profits and they won't like to get the business out of hand. What do you wish to say about it on a
That
lighter side?
uh, just 3 weeks ago, that's the good example of the one presenter mentioned about this kind of issue. So, for example, like Tesla in 2014. So when they had a problem for the bankrupt of this electrical vehicle, but President Obama supported Elon Musk $230 billion to let them try for electrical vehicle, and then he tried to make a commercial opportunity and then have a very good value of this Tesla car. But at the same time in Germany, so they had one electrical vehicle company which called Taco. So this Taco had the same destiny with Tesla, but the difference was the President Obama, he supported, invested, and then this Elon Musk, because he was very strong, the venture person to tackle this kind of issue. That's why reason the President Obama trusted him 100% and supported the government funding to Tesla. That's the reason why he was successful. But in European Germany, electrical
Yeah,
vehicle, Taco didn't get through that level, and they bankrupt. So that's the exactly the same. You need a very strong investor, strong trust, strong, the supporter to make this kind of challenging technology happen. Otherwise, even though you have a good technology, it's very difficult to put into the commercial level. So that's the lesson. You need a lot of connection, a lot of collaboration, a lot of innovation. It's all together. Also, you need the most importantly luck. Your log is also very important. So that's
thank
my
you.
view.
Thank you very much, Professor Sean. I think the audience have enjoyed, especially the far-reaching points which he has raised regarding the technology, the inventions, the innovations, and along with the application of those innovations with respect to the commercial market. So thank you very much, Professor Sean. I think let's just put our hands together for this wonderful lecture which you have given.
Thank you,
we
sir.
we invite you sometime, if you get time in future, you may kindly visit our place and grace us with your physical presence. that will be very much inspiring. Thank you very much once again and being part of it. Thank you.
Thank you. Thank you, everybody.
Okay, friends, the next presentation in line is entitled Advancements in Nano-Enabled Membrane Distillation for Sustainable Water Energy Environment Nexus by Professor